Hey, hello to everybody. My name is Sebastián Mantilla. I'm a student at Max Planck Institute for Complex Systems in Dresden, Germany, with Inti Sodeman, my advisor. And this is part of the research project that we are doing, in part, forming part of my PhD. So this poster consists of a method that we propose to do bosonization in systems that it is not usual to do it, like for instance Dirac Fermions systems. But before checking the method, it's important to have into account that perhaps some of you may know that when you use bosonizations, you apply them for system with only one band. Like for instance, this system with only one parabolic band, in which you have an excitation which consists of an electron above the Fermi level, the Fermi energy, and the corresponding hole below the Fermi energy. So you can understand this pair as an excitation as a boson, which has momentum described by Q, being Q the difference of the momentum of the electron respect to the hole. So you can have positive Q excitations and negative Q excitations. But when you create an excitation, it's impossible to create those ones with Q equals zero, with zero momentum. As we can check here in the particle hole continuum, that there are no states here with Q equals zero. But what about Dirac Fermion systems? In this case, we have not only Q different to zero excitations, but also Q equals zero excitations. And actually, these excitations are the most common ones in this system. So the majority of these states lie in this case for Q equals zero. The problem is that the usual bosonization method are not able to deal with this case. So in that way, we require a new bosonization method for a gapless Q equals zero excitations, like this one's observed in graphene, in the Dirac Fermi system, like for instance, graphene. And then the method is quite simple. It consists on, to begin with, assume a periodic boundary condition system. So then when you go to the momentum lattice, you obtain, to the momentum space, you obtain a lattice, actually. It would be similar to a real space lattice, but in the momentum space. And then we will focus only on Q equals zero excitations, not in Q different to zero excitations. So when you go to the momentum lattice, you can understand the Q equal to zero inactions as fermions that are occupying only one site, a single occupied state. And Q different to zero, doubly occupied or empty sites, because it would imply that the electron jumps from one K, from one momentum site to another momentum site. So it would leave a hole and a doubly occupied site by an electron that is in the valence band and the other one which is excited in the conduction band. So we focus only on singly occupied states, so Q equal to zero. And you may know that for singly occupied states, we can model the system with spin-like degrees of freedom in each one of the momentum lattice sites. So then, since there are only two states per site, it can be modeled as a spin-like degree of freedom. And then when we go to this part, we can then advance a bit more, and then using Hostin-Primakov transformation that allow us to model these bosons, these spin degrees of freedom as bosons. So at the end, we would obtain that each excitation can be described by a boson degree of freedom, like it is shown here in this cartoon, this simple cartoon. When we apply the creation operator of a boson at momentum k on the ground state, it creates a boson an excitation at momentum k. Quite simple. And when we apply the annihilation operator of that boson in momentum k to the excited state at momentum k, we annihilate. So in that way, this is the idea of proposing these bosonic operators. So what we do with this new boson degrees of freedom? But then we apply it to the Dirac Hamiltonian plus interactions, and we obtain this quite interesting Hamiltonian boson bilinear Hamiltonian. So the first term is the kinetic energy. The kinetic energy means how much energy costs to create a boson at site, let's say K, which is completely consistent with the original case because we obtain twice the energy of the electron after jumping from the valence band to the conduction band. So in that way, this is 2vk. It's completely consistent. But then we have three contributions more. The first one is a self-energy. So the cost of having a boson at momentum k also receive a contribution from the interactions, from the original interactions in the electrons, in the original degrees of freedom. And this self-energy will correct not the mass, because remember that these systems are gapless, but the velocity of the electrons in the system. So this self-energy will correct this parameter V. What is the form of the potential? It is this one. It's an UV damped Coulomb potential, where K is the UV cutoff. But also we not only obtain the self-energy, we obtain two fun, quite interesting terms that are a hopping term, which means that these interactions allow the bosons to jump from one momentum lattice site to another one. But not only it allows them to hop, it also pairs among them. So we can have only also bosons that are paired at momentum sites k and k prime, depending on the value of the angle that forms the two sides respect to the center of the column. And once again, this is the way in which the boson operators act on the ground state and on the first excited state at momentum k. But then, let's check the physical problem. There is a controversy in the value of the optical conductivity. We are focused only on Q equals 0 excitations because we want to obtain the optical conductivity for this system with that method. So it is well known in this research area, that the optical conductivity for free Dirac Fermions can be described by only fundamental constants of nature. So the electric charge of the electron and the reduced Max Planck constant. But when we introduce interactions, actually interactions described by this potential, we obtain these corrections. So at first order, we can understand it as 1 plus c times alpha. But by having into account other contributions of higher order, we obtain this full correction, which is actually the correction to the Fermi velocity. But let's focus only in this part for the first order. There are two proposals. The first one by Herbut et al. From 2010 that says that the value of C, of the constant C that weights the first order correction to the optical conductivity to the value of 0.51. But there is also another proposal, a bit older, from 2008, done by Mischenko, which says that the C has a value of 0.01, so almost 2 orders of magnitude smaller. It has important consequences to the experimental values that are measured of the optical conductivity. So depending on the method that it's used, there are two values. What is the correct one? That's what we'd like to check. And then how we do it? We built that Hamiltonian that I showed a couple of slides above before. And then by diagonalizing the Hamiltonian, we obtained the results. So eigenvalues and eigenvectors that are important to build the response function corresponding to the optical conductivity. And then this is the numerical results that we obtained of the corrections to the optical conductivity depending on the frequency. And then what we find is that this white line is the numerical results, and the solid constant lines, constant in frequency, are the first order corrections that are proposed by Bosonization et al. And what we find is that the value of C that make the results consistent is Mischenko's value. So this method is consistent with Mischenko's proposal of the value of C equal or approximately equal to 0.01. But not only the method is able to discern which value of C is the appropriate one for the system, but it also obtains the running of the optical conductivity with the frequency of the electromagnetic wave that it's colliding with the layer. And these dashed lines are these functions. So the method not only obtains the C equals to 0.1 constant, but also the running of the corrections to the optical conductivity with the frequency. So in that way, it makes us to think that this method could be quite useful on describing these systems. In that way, the method is consistent with Mischenko's value. But what about experimental results? This correction, as you can check here, is not larger than 4% of the full value of the optical conductivity. So it is a quite small correction. So let's check the experimental results to know if the system, if the method is consistent with them. And at the moment, the results lie in this regime. So it is still on more or less 10% of the value of the full optical conductivity. In this case, it is described as the absorbance, but there is a one-to-one relation with the optical conductivity. And our results proposes that the value is not above 4%, so that 4% is like the upper bound for the corrections. So we are still in agreement with the experiments. So what we would like to check is, by the improvement of the experimental techniques, if the Mischenko's constant not only describes correctly the optical conductivity, but also if the optical conductivity runs in the way that it's described by Bosonization from 1999, and especially if the dependence is described by the description that we obtained with the bosonization method. So this is the point at the moment in which we are. So we would like to check it, but in that way we should obtain wait for further experimental results with higher precision. And once again, thank you so much for your attention. We are so happy to receive your questions, to get your proposals, and feel free to write to us to our emails in the first slide. Thank you so much.